Hello, everyone. Aha. So, spotlight. Welcome, everyone. I hope you've seen this is the third assignment. Have you seen the third assignment? 1 for yes, 0 for no. Very good. Oh, nice. Come on. How come you haven't seen the third assignment? Oh, are you? If you are in the follow along group, then you wouldn't have seen it yet. Is anyone here from the follow along group? Raghav, not exactly. No, this is on an individual basis. No, the 19th that you have seen on the this is just for your tutor to enter your grades. I need to make that clear. But that's not we expected you to do it by the 12th, but if you haven't, just submit it as soon as possible. Here, as in here, you're in the follow along group. So what do I do? Let me think. Well, if you go to Canvas and you go, okay, I might as well show you Canvas because I have a feeling that some people are still not there yet. So student view. So when you go to Canvas, let me share my screen. There we are. This session is not mandatory. No, this is extra, and these sessions are recorded. So if you, if I don't know, if you have some kind of practice or if you have something to do at this time, you can watch the recordings afterwards. So when you go onto your Canvas, you're supposed to see just your year. Do you see your year, or do you see all 3 years? This would be valuable information. Do you see just all 3? Can you, if you go into year 10, for example, can you access the assignments though? You can't go in. Oh, yes. As in you can see all the assignments. Is that correct? You can't submit anything. Good. That's fine. Now if you go back, so if you go into year 12, you should be able to see the assignments. You have the assignment discussion group, which is where you can have a chat with everyone. You can also participate in other discussions. So if in discussion, you should be able to see your discussion group. When you click on discussions, do you see all the discussions, or do you see just your group? Just ours. That's good. That's good. That's important here. Okay, so and then that's home, and then you when you go to assignments, somehow I don't see the assignments here, but you should see them. Like this one, the due 12th of November. That's the one that that you are supposed to submit. The 19th is just for your tutor to add the grades, because just to add the grades separately. Okay, so when you, 12. Course calendar. Okay, so this is the 17th, on the 17th of December. And details. So when you go, here's the physics and the maths. Okay, so if you access a download file here, so I open a new tab and download file here. And here's the mathematics assignment. Here it is. And here's the physics assignment. I hope that makes sense. It's a bit clunky. Oh, okay, I didn't mean that, everyone. It's a bit clunky. But hope you'll get used to it. I'm still getting used to the new system, and apologies if yeah. So that's how Canvas looks like. Please log into Canvas if you haven't already. But I have a feeling that people who are here don't have any problem logging into Canvas. Yeah. Okay. The third assignment, I've just posted a link. Just right above you is a link to the third assignment. Okay. Right. And if you are in the follow along group, you will receive a link as soon as I plow through the 120 unanswered emails, which I still plowing through day and night. Literally finished at midnight last night. Anyway, so today we're going to talk about Newton's laws. And I have done 2 webinars at least on Newton's laws. So, and I've done really difficult questions. So today I'm going to focusing more on theory and medium difficulty questions. If you want to access the difficult questions, please watch my previous webinars. I hope you know where to find the link. It's on our website. Okay. Right. So that, and without any further ado, let's get going. I'll just make the chat bigger for myself. Right. Excellent. Okay. So today we talk about Newton's laws, and the Newton's first law says there exist reference frames known as inertial, in which an object remains at rest or moves with constant velocity if it's not interacting with other objects. This is a bit different from what you've studied in school, right? You've done Newton's first law in school, I believe. Is there anyone who hasn't done it? Type 0, please. Newton's first law. You should have done it in year 10. In school, you're taught that, if there are no forces, an object moves with constant velocity. So you only have the second part of it. An object remains at rest or moves with constant velocity if it's not interacting with other objects. This is what you already know. But if that were the case, do you remember Newton's second law? Newton's second law says F equals ma. And basically, if F is 0, then A is 0. So if you take Newton's second law, it actually follows. The version of the Newton's first law, which you're taught in school, follows directly from Newton's second law. So why would you need 2 different laws which basically do the same thing? Oh, apologies, just one more thing. The answer is that, well, of course you don't, because there's something more to it. It's the 15th. Okay, can you still hear me? Okay. All right. Okay. Reference frames. Good. Now, so Newton's second law says that F equals ma, and if you say if there's no force, if there's no force acting on the object, then there's no acceleration. So that means if there is no force, is no resultant force, we have constant velocity. Constant velocity. Because constant velocity is another way of saying that A is 0. Yeah, yes, sure. Do you understand that Newton's first law follows from the second Newton's law? Right? You understand all that? So type 0 if type 1 if you understand, please. Type 0 if you don't. Okay. So the question is, why would you need two different laws if they can do the same thing? Like, why not just say F equals ma and then forget about the first law? Well, actually, they've made it simpler because the concept of inertial reference frames is quite complicated. So they removed it. They swiped it out about 20 years ago out of the school program. And they said, nah, students don't need to know about it. Well, I'm here to change that. I think you do need to know that Newton's first law postulates the existence of reference frames known as inertial reference frames. What is an inertial reference frame? Well, an inertial reference frame is a reference frame in which Newton's first law is true. How does that work? Well, let's say, what is okay, let's answer the question, what is a reference frame? I saw that question in the chat. What is a reference frame? A reference frame is a set of rulers and timers that you use to measure your position. A reference frame is a set of rulers and timers that you use to measure your position. Relativistic reference frames. You could have a reference frame that is moving at a relativistic speed, yes. So you could have an inertial relativistic reference frame, technically. The opposite to inertial frames is non-inertial. Simply put, inertial. I will tell you what a non-inertial frame of reference is. So a reference frame is a set of rulers. So for example, my room, my office is a reference frame. I can measure my position relative to the cupboard, relative to the bookcase, relative to my lamp. I can say I'm 2 meters away from the lamp. I'm 1 meter away from that wall. This is my position. I also have a timer. I can measure the time. I can measure my speed moving through that room. And my room is an inertial reference frame. My room is an inertial reference frame. The deadline for the third assignment is the 17th of December. So you have just over a month to do. My room is an inertial reference frame. How do I know that it is? How do I know that? Do I know that? Well, because all objects obey Newton's first law. Simply put, this. Because that's what it says. There exist reference frames known as inertial in which an object remains at rest if there's no other force, if there are no forces acting on it. So I put what do I put? I put a small round object, a cylindrical object. I put a battery on my table, and if I don't push it, it doesn't move. No, that's, well, yes, I am also not moving. If I put a tennis ball on my table, it won't move. If I put a toy car, I'm not pushing it and it doesn't move. This is one example. A train traveling at constant speed, a train traveling at constant speed is an inertial reference frame. Because if you put something on the table, it won't move. If you drop something if you're standing in the train and you drop something, it won't fall directly downwards. It will not fly sideways. So I can just copy that statement. How do I know that? Because all objects, if you don't push objects, they don't move. This is a simplification, of course, but in an inertial reference frame, if you don't push an object, it doesn't move. It doesn't accelerate. Question is, can you think of an object where they don't, where that is not true? Can you think of a reference frame that you put something on the table and it accelerates? Raghav, very good question about the Earth. I will tell you about the Earth because it is tricky. It is both. It is both an inertial and a non-inertial reference frame. An orbiting body, very good. An orbiting body indeed is not an inertial reference frame. What else could be a non-inertial reference frame? An accelerating car. Very good. Yes. Imagine you're sitting in a car and you put a tennis ball on the dashboard. If you accelerate, the ball will roll backwards. Nothing's pushing the ball, but the ball will roll. Or in a car, if you turn right, the ball will roll to the left of the car, of course, not to the left of the road. So this is a non-inertial reference frame. So yeah, pretty much any accelerating system is a non-inertial reference frame. It gets very tricky with gravity. Gets tricky with gravity, but yeah, effectively, you could simplify and say an inertial reference frame is the one that is moving with a constant speed and not accelerating, and a non-inertial reference frame is a frame of reference that is accelerating. So going back to your question, is it Raghav? Raghav, you asked whether oh yeah, whether the Earth is a inertial or non-inertial reference frame. Well, the Earth is accelerating, of course, because it is moving in a circle around the sun. But this acceleration is so small that you wouldn't be able to feel it. It is very difficult to register. Also, the Earth is spinning around its axis, and you wouldn't be able to, you don't really feel it. But there are some things that happen on the Earth due to that effect. For example, in the northern hemisphere, the circles, the clouds form a right-hand spiral, and in the southern hemisphere, they go along a left-hand spiral. So if you watch some photos, Earth from space, Is there any better pictures? So yeah, so if you have a air moving from the north to the south, it's moving like this. It's a wrong diagram. No. Yeah, that makes coffee image. So the Coriolis effect is responsible for the cyclones, and they spin one way in the northern hemisphere and one way in the southern hemisphere, and this is because the Earth is a non-inertial reference frame. That's one example. Another example is the Foucault pendulum. Foucault pendulum. Do you have any videos? Pendulum time lapse. Here you go. So the Foucault pendulum is just a long pendulum. So it's a mass on a very long rope, and it just hops back and forth. But because of the rotation of the Earth, it changes the direction. So you can see that the pendulum swing changes direction because of the rotation of the Earth. So this is another example because the Earth is not technically it's not an inertial reference frame, but yeah, but the acceleration is so small. The acceleration is in the 10,000th of a meter per second squared, so it's just very small. Yeah, it does exist. You're correct, Rakhav, saying that the Earth isn't a isn't an inertial reference frame, but for most applications, it is, right? So when you're I don't know, building a house, you don't really take into account that the Earth is not an inertial reference frame because yes, you can assume that we're like in most cases you can assume that we're stationary. The Earth is stationary, and it won't change anything. Okay, so that's the deal with inertial and non-inertial reference frames. So let's give an example. An accelerating train. An accelerating train is not an inertial reference frame. Example: put a snooker ball on the floor. It will start rolling. Okay, and there's an interesting consequence of frames of a frame being inertial. In an inertial reference frame, there's no way of telling whether you're stationary or moving with constant velocity. If you are in an inertial reference frame, there's no way of telling if you are moving or stationary. Oh, because also being stationary is what is being stationary? Are you stationary now? Well, you're not. The Earth is rotating about 300 meters per second, and then the Earth is spinning 300 meters per second, and it's traveling around the sun at about 30 kilometers a second. So no, we are not. We're not stationary, but it's very difficult to tell, right? Just like in a train, sometimes you sit in a train and this train starts moving and you're not sure whether the train is moving or the other train is moving. So you're looking at a different train and so it starts to move and you're like saying, am I moving or is that the other train moving? So yeah, so there's no experiment that you can perform in a reference frame that will change that won't tell you whether you're moving or not. Of course, we're talking about if you can't see outside. If you see outside, it's obvious. Yeah, I'm moving. But if you can't look outside, you can't do any experiment inside the train that will show you that the train in fact is moving. Okay, so problem 2. Are there laws for non-inertial frames of reference? Yes, there are some. And we're going to do, and one of them is the Coriolis force. And the second one is centrifugal force. So these are the two forces that exist in non-inertial reference frames. Okay, so problem 2. The force acting upon an object is given by the mass times acceleration. So that's Newton's second law. You've known this is familiar. But how do we actually use it? Those of you who have done mechanics in maths, you should be more familiar with this. How to use Newton's second law? Well, first of all, I don't personally like writing it this way. I like to write it this way. Mass acceleration is equal to the resultant force. Or sometimes I say MA equals the sum of forces. And it's very important that you get yourself into this mindset, that how to use Newton's second law. So how to use Newton's second law? How to use Newton's second law? First, draw a free body diagram. And I mean it. It has to be a free body diagram. It has to be a proper free body diagram. Only one object should be present on your diagram. 2, choose a direction. And resolve the forces. And then 4, write MA equals F1 plus F2 plus where. So yeah, write Newton's second law. So let's have a look. So man on an elevator. What people start doing, they start drawing an elevator, the rope that pulls the elevator. Sometimes they even draw the motor, a winch that pulls the elevator. Then they draw the man. So the problem that we have encountered is that we only need to draw one object. So if we're talking about the man on an elevator, we just draw the man. Draw the man. Draw the forces acting on that man, and there are 2. There's the normal reaction force. There's the weight of the man, and there's the normal reaction force, and that's it. And now we don't know which way it is, it is accelerating, but let's say it's accelerating upwards. Then we choose the direction. We say up is positive. So this is an x-axis, and we say that MA equals the sum of forces, so N minus mg. This is how you write Newton's second law. So the total force is N minus mg. That's the resultant force. So MA equals N minus mg. Do you understand everything so far about Newton's second law on a scale of 0 to 10, please? So Archie, Raghav, Louis, Paris, Ethan, what would make it a 10? Can you ask me, please? How do I get it to a 10? What's the little thing? Okay. So there's something pushing you up, there's something pulling you down. And if you're accelerating up, that simply means that N is greater than mg. And your resultant force is N minus mg, which makes perfect sense. Self-selection issue in confidence score reporting. Yeah, there's definitely if n was always equal to weight, how would you accelerate? If you're stationary, yes, n is equal to weight. But if you're accelerating, then one of them has to be bigger. If you're accelerating down, okay, that's an important thing. Accelerating up, accelerating up, we have n is greater than mg. Accelerating down, n is less than mg. And if you have stationary or constant velocity, n is equal to mg. That is important. Okay. The same thing. Exactly the same way. You just need to you need to learn to identify the forces, because once you have written Newton's second law, everything else is math. So we've done the man on the elevator. So the common mistake here, what people do, they start drawing the forces on the elevator, they draw the tension force, they draw the normal reaction force here, the normal reaction force here, the mg here, the mg of the elevator, the friction forces on the elevator, and it becomes a mess. You're not supposed to draw, you're supposed to only draw one object and the forces acting on that object. And how do you know? Well, what is it? What is the object interacting with? Become the object and tell me what you experience. So if you're the man in the elevator, you experience a downwards force, the gravity, and the upwards force from the floor. And that's it. There's no other forces. You're not touching the rope. The rope doesn't have any effect on you. If the rope pulls the elevator, and the elevator is the lift, of course. Okay. The next example. Yes, you draw effectively two diagrams, and then you identify just the one. A car towing a caravan, and this is a good example. This is an example where you have a lot of forces. So you have a caravan, horrible invention. You have a car. I'm not very good at drawing, as you can tell. Okay, so the car is pulling the caravan. Okay, so you draw the caravan first. You draw the caravan first. So there's the gravity, where there's mg, m1g. There's a normal reaction from the ground. Normal reaction 1. Then there is the rope is pulling, well, the whatever that is, pulling the caravan. Let's call it T, the tension in the bar. This is the bar. Tension in the bar, T. We only have one bar, so we don't need T1. We just say T. Tension in the bar. And there is friction in the wheels. Of course, there's some friction always, F1. And we have some air resistance as well, FA1. Okay, let's call it F2, air resistance. Let's not make it a mess. F2 is air resistance. Okay, then you choose a direction. There are two directions here you can choose. You can choose the direction horizontal and vertical. So we can just write the x-axis and the y-axis. That would make sense. And you'd say, okay, so the x-axis. Mass times acceleration. So m1 is the mass of the caravan, m1, multiplied by acceleration of the caravan is equal to the resultant force. So the forces that help you accelerate and the forces that prevent you from accelerating. So it's T minus F1 minus F2. That's it. That's for x-axis. And the y-axis, m1 times a y in the y direction is, well, up minus down. So n1 minus m1g. But you're not accelerating. You're not accelerating upwards. So your upwards acceleration is 0. So this is 0. Therefore, n1 is equal to m1g. So you can use that. And here you've written Newton's second law for the caravan. Now the car. Now, if you talk about the car, this is the car. The same. We have the axes, x and y. We have the gravitational force, m1g, m2g, sorry, it's the mass of the car, m2g. Now there's the normal reaction from the wheels, n2, n2. We have the friction, we have the tow bar pulling backwards now, t. Because if the car is pulling the caravan forward, the caravan is pulling the car backwards with an equal and opposite force. So the tension in the bar. There is air resistance, of course. Let's call it F3. And there is friction force in the wheels, of course. Let's call it F4. What's the one force that we're missing? I'm approaching this force. It's a bar. It's a metal rod. Free Boy diagrams, you either draw from the center of mass or where the forces are applied. When there are multiple points of contact with the ground, I prefer to draw the normal reaction from the middle. But if I were to draw a box, for example, I would draw the normal reaction force here. Oh, sorry, the mg force here, and the normal reaction force here. I would draw it like this. You normally don't get marked down if you draw them from the wrong point, but just this is. So what's the other force on the car? The car's own acceleration. Yes. Now this is the trickiest force. When you say thrust, Caden, what do you mean when you say thrust? Who's actually pushing the car? Yes, driving force, Mena. That is correct. What do we mean when we say driving force? Ooh, Paris. Very good. Very good. Rotational reaction. Ooh, well, yeah, but this reaction has a name. That name is friction. It's the friction force that is pushing the car forward. I really want you to appreciate that. It's the road pushing the car forward. Yeah, so it's the road pushing the car forward, and yeah, so it's For friction, it's F5. Okay, it's getting really confusing. If the road is smooth, you can't move. You won't be able to drive on a smooth road. Imagine a car on ice. Doesn't work. Doesn't go. Okay, let's simplify this. Let's call these the resistive forces. F resistance. This is friction and the air resistance. And this is the friction force. F friction. So for the car, for the vertical, N2 is N2 minus M2G has to be equal to 0. Yeah, because the vertical, the y-axis, M2AY is 0. But for the x-axis, M2A, we don't need the x because, well, that's the acceleration of the car. The car is accelerating that way. It's the forward forces, F friction, minus F resistive forces, minus the tension in the bar. So this is Newton's second law for the car. Okay. The friction force causes the car to move forward. The last one is box on an inclined plane being pushed. Box on an inclined plane. Box. Okay. So let's say we have an inclined plane and we have a box. Very typical scenario. We want to know the acceleration of the box. Acceleration of the box. Let's let's say the mass of the box is 20 kilograms. There's a friction force which is 60 newtons. And the angle, let's say 30 degrees. Normal force. So yeah, you can. Now here, I mean, you don't have, well, it actually depends. So we draw the forces. We draw the forces on the box. And you could draw it separately. There's no shame in that. Just to get your head round. Draw the box separately. Although you can draw the forces here. Draw the box separately. The force is acting on the box. Well, there is the gravity, mg. mg. There's the normal reaction force. Reaction force. And somebody's pushing the box. Let's say somebody's pushing the box down with a force F. And is that equal to 100 newtons? Okay. So we have a downwards force of 100 newtons down the slope, and a backwards force of 60 newtons. That's the friction force. So we have F friction and the downwards force F. Now, when you're doing it along the slope, the best way is you don't have to do it this way, but normally you draw the x-axis along the slope, the x-axis along the slope, and the y-axis perpendicular to the slope. So here, and you can, I'll show you another useful trick here. So this is the x-axis, and this is the y-axis. Make a copy of that. I think I've shown this before. Make a copy of that, then just rotate. Okay, your gravity is not downwards, but now you have an x and y, which makes perfect sense. You split mg into components. This is mg, and this is mg. So I can forget about this one. This is mg cos theta, and this is mg sine theta, where theta is the angle. And now I can write the equation along the x-axis and along the y-axis. So the y-axis, well, it's not moving along the y-axis. It's not moving up or down. So I can just simply say that n is equal to mg cos theta. Along the x-axis, I write ma. It's accelerating. Yeah, it is moving. Ma is equal to forwards forces minus the backwards forces. So F plus mg sine theta minus F friction. I've written Newton's second law, and now I just use it to find the values. So I just substitute all the values in. So sub the values. MA, so 20 multiplied by A equals the full F is 100 plus 20 times 10 G times sine 30 degrees minus force of friction 60. So 20A is equal to 140, so 40 plus 20 times 10, that's 200. 200 times sine 30, that's 100. 100, so 20A equals 140. A equals 7 meters per second squared. That's how you do it. Normal force perpendicular to the friction parallel to the slope and mg directly downwards. Yes, Archie, thank you. Rakarov, aren't the sin and cos supposed to be the other way around? Is the cos theta and the x star? Maybe I'm really wrong here. Okay, now I see where you're coming from, because this angle is 30. And I always advise to draw a small angle, because if you draw 45, you don't know which one is which. So you have a right angle triangle. This is 30 and this is obviously 60, right? So a big angle and a small angle. And here, when you this, when you resolve mg, you can always tell which one is which. You can always tell which one is 30 and which one is 60. So this is 30. If this is 30, then this is the adjacent side. So this is mg cos 30, and this is mg sine 30. Yes, we assume g is 10. Rakav does, okay, that makes sense. So I always, when you draw an inclined plane, I always advise to do a small angle, because then when you have the forces, you know that this angle is theta, and then you do something like, all right, so I have a perpendicular component and a component parallel to the slope. And which angle do I need? Is this theta or is this theta? Well, the answer is obvious. This is theta. So it will help you. Although sometimes they tell you draw a nice big slope. This is horrible, because when you start drawing this, you see force like this, then you resolve the forces. Which one is theta? Is this theta? Then is this theta or is this theta? We don't know. So I always say draw a nice, draw a sharp, small angle. Okay. Okay, so this is how you use Newton's second law. This is like the biggest thing. So I've done lots of things, lots of well, I've done a couple of webinars on this topic. Newton's third law: when two objects interact, they exert equal but opposite forces on each other. Give two examples of pairs of forces. How is it linked to Newton 2? Well, we already saw one pair of forces. We saw the car pulling the caravan. So Newton's second law, action equals reaction, yes? So this is the force, the car pulling the caravan. And this was the caravan pulling the car. So the car pulls the caravan and the caravan pulls the car with the equal but opposite force. Okay, so car pulls caravan. Caravan pulls the car. The car with equal. Does anyone see a problem with this? Does anyone see a problem with this? Or does anyone see why would someone would have a problem with that? Yeah, it looks like the forces should cancel out. But this is why it is so important to draw only one object. The forces are equal and opposite, but they are applied to different objects. So paradox? I don't think so. I don't think so. There's nothing to do with constant velocity. Like Newton's third law applies for every single interaction. When you have a force, it is always a force between two objects. If there's one force, there's always an equal and opposite force. This is not a paradox because the forces are indeed equal and opposite. The forces are equal and opposite. But they are applied to different objects. So they have a different effect. They have a different effect. Does the car accelerate just because there are other forces acting? Well, yes. So they have a different effect. For example, why does my brain have gruesome examples? Imagine that you are cycling and you're being a little bit careless and you hit a wall straight on. So hopefully you had your helmet, but It still hurts. You hit the wall while cycling. So your head, the wall pushes your head. Yeah, when you hit the wall, when you hit the wall pushes your head, but your head also pushes the wall, and the forces are equal and opposite. They have to be, because Newton's third law says so, or in experiments so. Every single experiment we have done says so. Now, the forces are the same, but they have profoundly different effect. That force is enough to cause you quite significant harm, stop you from moving. You were moving, now you are not moving. But the same force applied to the wall has no effect whatsoever. The wall doesn't really care if you're pushing it or not. The force is not enough to move the wall. And this is the most important part of it. The car pulls the caravan, and this force is enough to move the caravan. But the caravan is pulling the car. That force is not enough to make the car move backwards. We have another force which is more significant, which is the engine pushing the car forward, which is more significant. So the whole system is moving forwards. Now, so let's have a look. There is a force on the caravan, and that makes the caravan move forward, and that makes perfect sense. If we look at the car, we have a look at the car. There is a force from the caravan. Yes, it is pulling you backwards, but there's a bigger force, the engine force, which makes you go forward. Archie, yes, excellent. The earth pulls us down, and we pull the earth up. And these forces are equal, but this force is enough to cause you to fall down. It is not enough to make the earth go up. They have different effect on the objects. So this is the resolution of the paradox, in big quotation marks, because there's no paradox whatsoever. Okay, then another example. Well, let's do the Earth and you. So the Earth and you. So this is you. This is the planet Earth. The Earth is pulling you down, and you are pulling the Earth up. Earth pulls you down with a force of, let's say, 500 newtons. Pulls you down, and you pull Earth up with 500 newtons. The Earth doesn't really care about the 500 newton force, so it doesn't move. You move, yes. If you fall, if you jump, you move. Okay, Neil, how can you explain how the tension works with this whole idea? The car pulls the linkage or rope connected to the caravan, and the caravan pulls the car using the same linkage rope. Would that mean that the tension in the rope is zero because the forces cancel out the same object? Does that seem intuitive? That doesn't seem intuitive, since there is a clear tensile force acting to stretch that rope. I wasn't here for the start, so I'm not sure if there is a rope. Yeah, there's a bar, but it doesn't matter whether it's a bar or a rope. You know, the tension in the rope is not zero. That's an excellent question. Can I get back to this? Can I get back to you after I've done one more example? So the following is not an example of Newton's, not an example of Newton's third law. You have a box. There's gravity pulling the box down. And there's the normal reaction force from the ground. The forces are equal. They're opposite. Why is this not an example of a Newton's third law? They're not of the same type. Very good. They're same type. No, they're not the same type. This is a gravitational force and this is an electromagnetic force. Mg is gravitational. N is electromagnetic. And what is the biggest thing here? Why is this not a not an example of Newton's third law? Yes, applied to different objects. That is not the case. They're applied to the same object. Caden, thank you for asking. Okay. If you take two charged objects, I'm going to take two magnets. I'm going to take two magnets. This is one of the things I recommend you watching. Richard Feynman on magnets. So you have two magnets and you push them together and they repel. In a very similar way, a negative object will repel a negative object. So a negative and a negative repels. Now, when you like this force, this force that you feel here, is the magnetic force, which is an electromagnetic force, of course. Now, when you push your finger on the floor, on the table, your finger is made of atoms, and the atoms have a positive inside and a negative outside, right? A negative on the outside. The table is also made of atoms. It's positive on the inside and negative on the outside. The atoms are. So whenever any two objects touch, now touch is another interesting concept, because what do you mean by touch? Yeah, because can any two objects actually touch? Can atoms actually touch? The answer would probably be no, not really. Unless they are in they form a chemical bond. So yeah, we have negative on the outside, negative on the outside. When you push your finger through the table, that's the electrostatic repulsion of the electrons in your finger and the electrons in the table that is not allowing you to push through the table. So this is an electromagnetic force. So when you push the table, you feel the normal force, and that normal force is electromagnetic because it's the repulsion of the electrons and electrons. So this is okay. Does that make sense, Caden? Okay. Yes, these are different types of forces, and there are only 4 types of forces in the universe. There's gravitational, electromagnetic, weak, and strong. So weak and strong, you've never experienced those in your life. So there are only two types of forces that you can feel. There's electromagnetic and gravitational. Whichever is not gravitational is electromagnetic. So all the forces we were doing and we will do so in this course, we're only doing two types of forces, electromagnetic and gravitational. So friction is electromagnetic, like tension is electromagnetic, etc. All forces except gravity are electromagnetic. As far as real life objects are concerned, only when you go to a subatomic level, you talk about the weak force and the strong force. Now finally we get to the question about the tension. Yes, tension is a difficult concept because you have a rope and you pull the rope on one end with a tension T, with a force T, and you pull the rope on the other end with a force T. So is the tension in the rope zero? Well, intuitively you will understand no. The acceleration of the rope is indeed zero because the resultant force is zero. So the acceleration of the rope is zero. Yeah, that makes sense because yeah. So T1 has to equal to T2. T1 has to equal to T2 because let's say if the rope has zero mass, because usually we talk about massless ropes, because if it wasn't true, let's say T1, if T2 was greater than T2 was greater than T1, there would be a resultant force and the acceleration would be infinitely large. Yeah, it is accelerating, but if you assume that it is, if you assume that, okay, if you assume that the rope is massless, and that's what you usually do, the rope is massless, and acceleration, let's say acceleration is 7 meters per second squared, then mass acceleration equals to the resultant force. So 0 times 7 equals resultant force. So resultant force is always 0. So on a massless rope, acceleration, the resultant force will always be 0. Resultant force on a massless rope is always 0. Yeah, when we talk about the bodies, the rope is not one of the bodies, right? We're not interested. We never write Newton's second law for the rope. The rope is just a means of pulling something. So we're not particularly interested in what happens in the rope. But T1 is always equal to T2. So the resultant force is always 0. But the tension. So you can think of the rope as being made of different pieces. And for every single piece of the rope, we have T1 here, and T on this side, T on this side, T on this side, and they are exactly equal. If this is T, you have T on this side, T on this way, T this way, T this way, T this way, T this way, etc. So the tension in the rope, when we say tension in those, is the tension between any two parts of the rope. It's the pulling force between any two parts of the rope. T is the force between any two parts of the rope. That's why we say the whole. Okay. For a light rope, tension is constant throughout the rope. For a real rope, the tension, yeah, if you have two equal forces, the rope would be stationary, as any object would. So for if you pull the rope here with a force T, this piece pulls this piece with a force T. But this piece pulls the first piece with a force T. And that's why the first piece is stationary. And the second piece is being pulled right, but it's also being pulled left by this piece. So the second piece is stationary, and so on and so on and so on. I think you're overcomplicating things. Like imagine a train pulling a car, and a car pulling another car and another car. Okay. So yeah. Between any two parts of the rope. So I mean, as any question with tension is concerned, tension is the force in the rope. It's the force between any two parts of the rope, and the tension is always the same at any point. For the rope, what are the force balancing out with mg to avoid it accelerating upwards? You mean for a heavy rope? Because in our example, the rope doesn't have any mass. It is massless. You're talking about a heavy rope. A heavy rope will never be horizontal. If you take a heavy rope, it can never be like this. It will always be bent. And you have a mg here. And the tension is not horizontal. Tension and tension. So you have two tensions, and the two tensions balance out the mg. Does that make sense? Because otherwise it is not. Was that a question from the assignment? Probably not. Well, there was a similar question. There was a similar question in the assignment one, but it was harder than this one. Okay. From all the forces, one of a fascinating force is Neil. Yeah, that's exactly it. That is the tension at the bottom. So you cut the rope in half at the lowest point, And there's the tension to the left, tension to the right. So that you got it right. I think you got right because not many people actually got that. So if you cut the rope in half, you have tension here, tension here, tension here, tension here, M1G here, and M2G here. So you just write them for two different. So this is assignment 01, problem 12. And you just, yeah, split them into components. Friction is an interesting force. Friction is an interesting force. So if you go bed motion, if you have a box on the ground, what is the friction force on the box? What is the friction force now? Can somebody tell me? Why? How do you know that friction is 0? Yes. It is, no, it's not proportional to velocity. The friction force, there's no friction force because if there was a friction force, it would be moving. As simple as that. There's no friction force because, yeah, it would be moving. So values, masses. Okay. So let's push the box. If I push the box with 1 Newton of force, the friction immediately becomes 1 Newton. And the box is still stationary. If I make it 51, it's still 51. It becomes 51. If the applied force is 52, the friction force will be 52. So as long as I'm not pushing, as long as I'm not pushing hard enough to make it moving, it will not move. And the friction force will always be exactly equal to applied force. Otherwise, it would be moving, right? So the friction force will always match the applied force as long as the box is not moving. And then at some point, when the applied force becomes 126, the friction force drops to 94. And let's graph that friction force. This is the applied force. Applied force. And this is the friction force. Okay. So if the force is 10, it would be 10. If it's 20, it's 20. 30. Well, let's make it 20. 40, 60. So at some point, it reaches a maximum and then suddenly drops. So the friction force behaves like this. And then suddenly it drops. So this is what we call this is friction max. So if you, the applied force is exactly equal to the friction force is exactly equal to applied force until you reach 126. And then the friction drops to 94. And it remains 94 even if you increase the force or decrease the force, it will remain 94 as long as it keeps moving. So you see, I reduced the force to 65 and the friction is still 94, and now you're slowing down. You're slowing down. And once you stop, friction becomes 65 again. Yes, thank you. Thank you for posting the third assignment. Okay, so it drops and then it is constant. It is constant. If you keep increasing the applied force, it is constant. So the maximum force, the maximum friction force, is known as is the mu s times the normal reaction force, and this force is equal to mu dynamic times normal reaction force. Now, in practice, it's slightly more like this, but yeah. So mu s is the coefficient of static friction and mu n is the coefficient of mu d is coefficient of dynamic friction. So the friction force is quite interesting. How come the different coefficients? Well, if you imagine if you imagine a heavy table standing on a carpet, once it stands for a long time, it kind of sinks into the carpet, gets deeper into the carpet. And it's harder to get it moving when it actually starts moving, it becomes easier to push it. So once something is already moving, it's easier to push it rather than when it is stationary. Well, yeah, you think of it, even smooth surfaces, they're not actually smooth. They have roughnesses, right? They are like they have a very good example, a very good idea about surfaces is like Velcro. If you imagine Velcro, if you put two Velcro, the longer they stay on top of each other, the closer they get. Yes, so it's harder to rip them apart. And then if you have, even for smooth surfaces, the coefficient of friction is still, well, I mean, we're not talking about smooth surfaces with zero friction. There's no, we're talking about small friction. Yes, so smooth means low friction. Okay, so that's it. Unfortunately, I have to go. I will carry on in 2 weeks' time. Okay, so on the 29th of November, I'll continue talking about friction. So I have to leave you now. Thank you very much. Bring your questions next time. All right, see you.